Hello everyone. Today's topic of my presentation is based on the Chapter 1 of Introduction to MMIC Technology book. This book is written by Professor MMIC. Here are the main contents. First of all, I will introduce the review to MMIC technology. This part includes Introduction to MMIC technology, definition of MMIC, history of MMIC, comparison between MMIC and hybrid MMIC, fields of application for MMIC, major boundaries of MMIC. Then I will introduce materials and devices of MMIC. This part includes MMIC materials, MMIC active devices, MMIC passive devices. This part is the review of MMIC technology. As we all know, RFIC technology is widely used in various wireless systems, encompassing RF front-end, WAN, bio-wireless applications, LAN, and DBS. RF modules or systems can be integrated for diverse mobile applications. MMIC technology integrates fabricated active and passive components on the same semiconductor substrate. Current IC technology trends focus on high-speed performance and low power consumption. MMIC technology provides essential components for wireless communications, including microwave and millimeter wave communications, satellite communications, and military applications. It has gained widespread acceptance among major wireless and broad communication equipment suppliers as the preferred technology for high-frequency, high linear applications. MMIC are now used extensively in communications, radar, bio and RF sensing systems. In this chapter, a definition of MMIC, the advantages and disadvantages of the MMIC, the history of the MMIC, a comparison between MMIC and hybrid MMIC, and several applications of MMIC are described. First is the definition of MMIC. MMIC are integrated circuits for high-frequency applications like mobile phones. They combine transistors and passive devices on a single chip, serving as amplifiers and filters. They operate frequency ranges from 1 GHz to over 100 GHz. In the next is the history of MMIC. This part includes three parts. First is origin of MMIC, then is key milestones, and the third one is impact and applications. In the first part, origin of MMIC. MMIC technology originated from a 1964 government-sponsored project at Texas Instruments. It shares roots with silicon, monolithic, and digital IC technology. In the second part, key milestones. Silicon integrated circuit technology was initiated in 1964 for a phased array radar antenna. In 1968, Michael and Wacker fabricated a 94 GHz front-end receiver using a semi-insulating gas substrate with some people. And in the third part, impact and applications. MMIC technology advancements facilitated various commercial applications, including DBS TV receivers, ACER, wireless local area networks, and personal communications. In this part, A comparison between MMIC and hybrid MIC is provided in the left table, focusing on size, cost, reproducibility, reliability, and performance. And the right table presents the advantages and disadvantages of MMIC compared to hybrid MIC, covering aspects like cost, performance, and size. This part is the application field of MMIC. There are many fields of application for MMIC. Table 1.5 presents the military, civil, and space fields along with a list of their applications. We can see in military, MMIC can be used such as in SAR, smart munition and decoys, electronic warfare, and in space, it can be used in satellite TV receiver, satellite for communications, and in civil it can be used satellite TV receiver, wireless communications, and so on. This part is the materials used in MMIC. In this part, the various substrate materials C, gas, SIG, SIG used in MMIC technology are described along with active devices, such as the gas MESFET, gas HEMT. Furthermore, passive devices including inductor, capacitor, resistors, transmission lines, dividers, combiners, isolators, wire hose, air bridges metals, and wire bonding and pads are also presented. In the next, we introduce these materials briefly. C is the most popular substrate material for chip manufacturing. It has high strength and excellent passivation layer, resulting in high yield and low cost devices. Gas is a high-speed substrate materials for semiconductor chips. It is suitable for microwave components enabling application at frequencies exceeding 25 GHz. And SIG is an alloy of silicon and germanium, offering improved transistor performance. SIG HBT technology developed in 1987, initially for high-end computing. It has lower cost compared to gas devices. SIG is a wide bandgap material with high electron saturation velocity. It is suitable for high temperature, high speed, high frequency, and high power applications. GaN is a wide bandgap semiconductor with applications in of electronic, high power, and high frequency devices. It's used in LEDs since the 1990s and wireless laser diodes. This part is the active devices of MMIC. A number of technologies have been developed for MMIC, including gas MESFET, gas HEMT, GaN HEMT, gas HBT, CBJT, SIG HBT, and so on. The material choice for an MMIC application is dependent on the electron drift saturation velocity, mobility, and resistivity, among others. The main active devices for MMIC are explained briefly in the following. First is the gas MESFET. Figure 1.1 illustrates the structure of the gas MESFET and its equivalent circuit. Most gas MESFET devices operated in deployment mode, requiring negative voltages to control the gate. Enhancement mode devices with a shallow channel only need a single polarity supply, and higher saturation electron drift velocity in gas allows for faster device operation. Gas MESFETs are easily fabricated using ion implantation in mass production, and current devices on the market have gate ranges ranging from 0.8 μm to 0.25 μm. This part is the gas HEMT. The left figure already shows the basic structure. It utilizes a two-dimensional electron gas structure in the active layers, typically provided as an epitaxial wafer. It incorporates single or double heterostructure transitions to achieve high electronic mobility in the 2D. And epitaxial layers are most grown by MBE, with some MOCVD. Its gate length requirements vary, with as low as 0.112 μm needed to achieve transmit frequencies up to 100 GHz, although 0.5 μm is also used in some mobile applications, and it offers the lowest noise figure and high gain, but may exhibit strong oscillations, making it less suitable for low-frequency applications. This part is the gas HEMT. It is increasingly attractive alternative to IMP-based HEMTs for low noise and low power applications. It utilizes metamorphic device structures which involve the growth of IMP-based structures on gas substrates. It incorporates a compositionally graded buffer layer to expand the lattice constant, intentionally forming crystalline defects confined mainly to the buffer layer. It enables the growth of IMP-based structures on gas substrates, which are available in larger diameters and at a lower cost compared to IMP substrates. Figure 1.3 shows the schematic cross-section of a metamorphic HEMT device, illustrating its structure and components. This part is the GAN HEMT. The key issue for HEMT operation is the heterojunction interface between semiconductor materials with different band gaps. The ALJN is grown on top of JN, creating a heterojunction. And figure 1.4 illustrates the conventional expressible structure of basic ALJN JN HEMT, highlighting key components and layers. This part is the compound HBT. Modified version of BJT with a wide bandgap emitter and narrow bandgap base region. Figure 1.6a provides the structure, and it highlights the emitter and base origins. This part is SIG HBT. First, we need to know the C and G. C and G have diamond lattice structures, and the G lattice constant is 4% greater than that of C, and the emitter has a wider bandgap than base. Next is the characteristics of SIGA. SIGA has a lower bandgap due to different lattice constraints. The electron mobility in SIGA is approximately 2 times faster than C. And the figure 1.7 illustrates the main structure and bandgap diagram of SIGA HBT. This part is the CBJT. The schematic diagram of CBJT is shown in the figure. These devices are capable of achieving a transmit frequency up to 25 GHz. The typical features include emitter width of 0.4 μm and utilization of double polysurf-aligned technique and sidewall spacer technique, and incorporation of buried layers and selectively implanted collectors. There are some advancements in CBJT technology. Even more advanced CBJTs with frequency up to 24 GHz, such as the Siemens B6 HFE, can be achieved by stretching the emitter width. This part shows the last active devices of MMIC. Now let's see the passive devices of MMIC. Passive components are used in MMIC layouts and designs for impedance matching, DC biasing, phase shifting, filtering, and many other functions. This section presents a description of the passive components used in MMIC design. First is the inductor. MMIC inductors can be realized using straight narrow tracks, single-loop inductors, or multi-turn spherical inductors. The choice of inductor for a circuit is dependent on the required inductance and its implementation in the circuit. Considering a microstrip ribbon inductor with its equivalent circuit as shown in the below figure, its inductance and shunt and capacitance can be calculated using the following equation. Here introduce the microstrip ribbon inductor, loop inductor, and spherical inductor. This part is the capacitor. First is the MIM capacitor. It comprised of two metal plates separated by a dielectric material. The dielectric material overlaps the first metal layer, with the upper metal layer having a smaller area than the lower metal layer to minimize fringing effects and shorts. It typically used for capacitance values below 1 pF, and it primarily utilized for blocking DC. The equivalent circuit is depicted in Figure 1.11. The next is the interdigital capacitor. It consists of multiple pairs of interdigited metal fingers separated by a dielectric material. It provides capacitance values typically below 1 pF due to its size and distributed effects. The choice of capacitor depends on the required capacitance values and other design considerations. This part is the resistor. First is metal thin film resistors. It consists of thin films of low thin metals like tin, thermite, and nickel. The advantages include low temperature, coefficient of resistance, tight tolerance, small parasitic effects, and low sheet resistivity. And the next is gas-based resistors. It is implemented using the FET channel and MMIC contacts already available in the MMIC fabrication process. The resistance is controlled by the doping concentration of the gas substrate, and the challenges include current handling capacity, thermal dissipation, and distributed effects. This part is the transmission lines. First, let's see the definition and the purpose. Transmission lines and waveguides guide energy from a source to a load within a circuit. They can consist of conductors, dielectrics, or combined self. Next is the types. The microstrip transmission lines are commonly used in MMIC due to their ease of fabrication and integration. The coupler waveguide transmission lines are also used in some cases. The figure shows the structure. This part introduces the combiners and dividers. The combiners are used to merge two or more transmission lines into a single transmission line. The dividers, on the other hand, are utilized to split a microwave signal from one transmission line into two or more transmission lines. The principle is microwave signals can be combined or divided using T connections of transmission lines. And in power division, an input signal is divided by the coupler into two or more signals with reduced power. The types of couplers. Couplers can be categorized into 3-port or 4-port combos. 3-port couplers include T-junctions and other power dividers, while 4-port couplers include directional couplers and hybrids. This figure shows various types of coupler lines. This part introduces the isolators and circulators. An isolator permits the passage of microwave signals in one direction while blocking them in the opposite direction. This functionality is achieved using ferrite material with a ferrite metal mounted inside the waveguide. An external magnetic field typically supplied by a C-shaped permanent magnet magnetizes the ferrite. The most crucial specification for an isolator is its isolation characteristics, which denote its ability to attenuate signals traveling in the undesired direction. The circulator directs microwave signals from one port of the device to another in a sequential manner. For instance, if a signal enters port 1 and exits at port 2, then a signal entering port 3 will not be routed to port 2 but instead will exit through port 1. The primary consideration for a circulator is its insertion loss, which quantifies the signal attenuation as it passes through the device. This part introduces the wire hole. The wire holes are utilized to establish electrical connections between different metal layers within integrated circuits. These connections facilitate the transmission of signals and power between various components of the circuit. Through-wafer holes or wire holes are employed to electrically connect both sides of a silicon wafer. This configuration finds applications in three-dimensional packaging, micro MEMS, and multi-chip stacking. The figure 1.16 is an ideal wire hole in the gas substrate. This part introduces the metal air bridge. An air bridge is a metallic bridge structure that permits the crossing of transmission lines on an MMIC without causing electrical interference or short circuits. It ensures that signals can pass over one another without interference, enabling complex circuit layouts and compact designs in MMICs. The fabrication of air bridges involves several steps. First is metal deposition. The second is photoresist patterning. The third is gold sputtering. The last one is metal plating. And the reliability of air bridges depends on several factors including bridge metal thickness, contact or post size, bridge height, interconnect metal, bridge length. This is the last one, wire bonding and bond path. Wire bonding is a common method used to establish electrical connections between MMIC and external components of security. Bond paths are designed areas on the MMIC where wire bonding is performed. They provide a secure and reliable connection point for attaching wires. The right figure shows the structure of the wire bonding and bond paths. My presentation is it. Thank you, everyone.